We began with radio noise that we couldn't explain. At first, we thought it came from our 20-foot horn antenna.
The horn was designed and built at Bell Laboratories for satellite communications research, but we were using it temporarily for radio astronomy.
We tried to locate it in the horn, and then out in space.
For Bell Labs scientists Arno Penzias and Robert Wilson, that tiny bit of noise sparked an all-out search. 2 years after their search began, they found its source. An unexpected bit of warmth, just 3 degrees above absolute zero, that fills every corner of space. Their discovery confirmed the Big Bang theory of the explosive origins of the universe. Arno Penzias describes those origins.
Billions of years ago, all the matter of the universe, a compressed, hot, dense, primordial energy soup, exploded. Every particle of light and energy rushing away from every other particle. After a few seconds of expansion, the universe cooled to 3 billion degrees, and the particles began to combine with one another. The universe went on expanding and cooling for several 100,000 more years until the temperature dropped to the point where atoms could be formed. Atoms later fell together slowly to form the giant gas clouds of hydrogen and helium. The clouds eventually collapsed under their own weight to form young galaxies. Billions of stars were born in billions of galaxies. The universe continues to expand, increase in size by hundreds of thousands of miles a second. The heat of the fireball continues to cool. Today, the background temperature is 3 degrees, and the distances and velocities of the galaxies that we now observe are all that remain of the Big Bang.
How could a telescope built for satellite communications help astronomers put together this story of the origins of the universe? What was the history of events that led up to one of the most important discoveries in astronomy? Robert Wilson continues the story.
In the 1920s, Edwin Hubble, using a large new optical telescope on Mount Wilson, photographed and measured the distances of galaxies, those giant islands of billions of stars. Hubble discovered that the greater the distances of the galaxies, the greater their speeds away from us. The universe seemed to be rapidly expanding. Astronomers asked why. It took close to 50 years to explain the flight of the galaxies. Shortly after Hubble's discoveries, a group of Bell Labs engineers in central New Jersey were working on transatlantic radio telephone circuits. They were trying to understand the noise or static in them. Bell Labs asked one of its young staff members, Carl Jansky, to locate the noise. Jansky studied the problem. Then he built a directional antenna, a rather strange-looking array of lumber and hardware. He mounted it on 4 rubber tires so it could rotate. It looked like the wreck of an old biplane. The steel rods of the antenna were wired to the receiver, which in turn drove the pin of a moving paper recorder. The contraption made a complete scan of the horizon every 20 minutes. Jansky found that lightning and thunderstorms was the source of most of the static. But there was one steady, hiss-like noise that he could not identify with storms. When he looked back at his records, he realized that the hiss started a little earlier every morning. It was moving with the constellations. It belonged to the distant sky. He then was able to find the region of the sky the hiss was coming from. It turned out to be the center of our Milky Way galaxy. The hiss was traveling 50,000 light years to enter Jansky's antenna. In searching for transatlantic telephone static, Jansky had located the first extraterrestrial radio source. He had also invented the radio telescope, and that was to open a whole new view of the universe. After World War II, engineers were able to build bigger and more sophisticated radio telescopes. In addition to stars, astronomers could then study the invisible clouds of gas between the stars and galaxies. Meanwhile, employing much the same technology, horn reflector antennas mounted on top of towers were being used to relay telephone conversations. A larger version of these horn reflectors was built on Crawford Hill in Holmdel, New Jersey, for an exciting new use: satellite communications.
I came to Bell Labs in 1961 straight from graduate school. I had done research in radio astronomy there, and I wanted to continue that work. At the same time, however, I wanted to do something practical as well. And here at Bell Labs was an ideal place to combine those two. The possibility of satellites for communications overseas had been foreseen by John Pierce. Telstar was the first satellite built to receive, amplify, and transmit signals spanning continents, oceans, space. 100,000 components were packed into an incredibly complex 3-foot diameter bowl.
Open solo fuel. 3, 2, 1, 0. Start.
Telstar was a great success. The first telephone conversations were sent overseas by satellite, as well as the first television images, including those of President John Kennedy.
I understand that part of today's press conference is being relayed by the Telstar communications satellite to viewers across the Atlantic, and this is another indication of the extraordinary world in which we live. So we're glad to participate in this operation, developed by private industry, launched by government in admirable cooperation.
While the main job of the 20-foot horn antenna was to stand by during the Telstar operation, we were able to do some other useful satellite research with it during that time. The design of the horn and its sensitive receiving equipment was also ideal for certain kinds of research in radio astronomy.
At the time I came to Bell Labs, satellite experiments with a 20-foot horn reflector were just about over. I wanted to use it for about the same purposes Arno did.
I come from a big city. I come from New York, where people don't mince words very much. Bob, on the other hand, is a Texan. I guess anybody who's seen a John Wayne movie knows what that means. The amount of output, the amount of information per unit time is probably about the same.
We could have worked separately on our projects, but we both wanted to use the same instrument and, by and large, do the same projects. Therefore, we decided to work together.
I'm much happier with a blackboard and order of magnitude calculations than I am with a computer with a lot of decimal places. That's one part of an approach, and the other part of the approach is needed too, and that's where Bob comes in.
Arno had a background in low-temperature physics. He'd built masers before, and I had much more of a background in electronics.
And together, the two provide something that neither one of us could provide alone. I think we respect each other, and we respect each other's talents, and we approach problems from both directions, from both things at the same time, and we're able to find solutions which neither approach could find by itself. When the horn became available for radio astronomy, it needed additional tools. The first was something to compare the sky against, a faint but well-understood standard source of radio noise, something we call a cold load. With my experience in building low-temperature receivers, I was responsible for making the cold load. This was largely a trial and error, hands-on process. Making sketches, building parts, testing, doing more sketches, and then getting everything built. The cold load is cooled with liquid helium, the coldest common substance that we can use for an experiment. I started out by designing the best load I could, regardless of size, and worried about cooling it later. It turned out to be so large that we ended up putting it in something like a giant thermos bottle.
The other main piece of equipment we needed was a switch to connect the receiver to either the cold load or the sky. The switch was designed to make the comparison of those two to an accuracy of a couple of hundredths of a degree Kelvin. I still have the switch and some of the pieces I used in making it. I started out calculating how much I would have to bend this pipe to accomplish the switching. The bend is what makes it a switch. So I hit upon what I thought would be a workable design. In those days, there were no electronic calculators. I then had the shop make a piece of precision waveguide with connections on both ends. Then I put it in the press and squeezed it down the amount I thought it should be squeezed. A simple piece of circular pipe wouldn't do anything when you rotate it. But when you bend it the right amount and then rotate it, the radio waves can enter from either one direction, the sky, or the other direction, the reference, the cold load. A few years ago, Arno and I went back to the Horn antenna to talk about and reenact our 1964 and 65 experiments.
We set out to measure the temperature or radio noise in regions of the Milky Way using the telescope as a large thermometer. All objects emit radio noise. The hotter the object, the more noise. We had the receiver in the small cab mounted on the telescope, and we rode around with it. The measurements we made in those days were really quite simple. We compared the noise or temperature from different regions of the sky with the temperature of a liquid helium-cooled source, my cold load. Space is really very cold, close to absolute zero. The only common substance we have that's as cold as space is the liquid helium. Well, the first time when we bolted my cold load up to that low noise switch and got everything going and turned on the chart recorder, the first day everything was working perfectly, and then we switched down to the cold load. And we switched to the sky. We found, to our surprise, that the pen went up to the right instead of down to the left. The sky was about 3 or 4 degrees too hot. The first thing I felt was really relief, because I said, well, my cold load is pretty cold after all. But then we thought about it. Here was this weird result. Once we found that radiation of an unknown origin was coming into our antenna, we tried to pinpoint its origin, and so we looked day and night in case it was coming from the sun. I'm switching back the load now. Switch to sky. Switch to the load.
The effect was the same day or night. That certainly didn't make any difference, and from one season to another didn't make any difference. I'm sure we came within 10 or 15 degrees of all of the sky that's visible to us here.
Load again. Back to the sky. Unload. Sky. Load. We looked out of the plane of the planets to see if it had anything to do with the solar system. We looked away from the Milky Way to see if it had anything to do with our galaxy.
And except for known sources, we didn't see any increase or decrease in the temperature of the sky.
Man-made interference was another thing we checked for. For example, automobile ignition provides an electrical noise which can be picked up by sensitive receivers. So we checked by moving the antenna carefully along the horizon.
And we nibbled away bit by bit at those possibilities.
But in none of these cases was there any change at all. That's what made it so puzzling. Because if there had been some source, at least, we could trace its origin. But there was nothing out there to which we could assign the origin of this radiation. After a while, we felt that we were going around in circles. We weren't doing research on the Milky Way galaxy. We were wrestling with a slight bit of warmth or noise. What would people think if we were to publish this result? When we started out, it was a nuisance. Then it got to be a puzzle, and finally an embarrassment. We checked to see if we were picking up warmth from the ground instead of the sky. We put a small signal generator on a cart and wheeled it around to see if the antenna was picking up anything from the surrounding area. It wasn't coming from the ground. What else did we try?
Even to be sure, we got up in the antenna and taped over the joints. The antenna really was about like a solid piece of aluminum. I thought that it might be right in the throat section of the antenna, and so we changed that piece. I guess we tracked down lots of other things. Then the only thing left that seemed possible was the pigeons. You remember that pair of pigeons nesting in the horn? We couldn't get rid of them. Every time we walked up near the antenna, they'd fly away. As soon as we went away, they'd come back. So finally we had to catch them with a have-a-heart trap, take the antenna apart, clean up the mess, hopefully the source of the problem. I didn't mind cleaning up after the pigeon, of course, depending on who's uphill with the broom. But you know, in some ways, it was a welcome relief from worrying about the noise. We put it all back together again, and instead of 4 degrees of noise, we now had slightly over 3 degrees. Then we were really stuck. We eliminated just about everything, and then the only possibility was that it was coming from someplace outside our galaxy, and that seemed like such a far-out idea. We just didn't know what to do with that result. And then you talked to Bernie Burke,
and he told me about this paper of Peebles, this preprint that he had seen. And so I called up Bob Dickey at Princeton, and he sent me a copy of it. Dickey came over and told us that they were making a measurement to look for something like this.
and I think we convinced them at that time that we had really measured the background temperature, the remnant noise from the creation of the universe.
This idea of a remnant noise had first been put forward by George Gamow, Ralph Alpher, and Bob Herman. Our discovery and its identification can be taken together with the flight of the galaxies and other evidence to provide a story of the birth and evolution of the universe.
Because of the profound implications of their discovery and its importance in astronomical research, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics in 1978. What do scientists do after making one of the most exciting discoveries and winning a Nobel Prize?
Within walking distance of the old horn antenna, on the same hill, we built a new 7-meter telescope. I spent a good deal of time designing this new telescope. It was built for use with radio beacons added to the Comstar communication satellites. We're trying to increase the capacity of new satellites by experimenting with higher frequency radio signals. The telescope is designed so that when it's not being used for monitoring satellite beacons, we can switch over very easily to radio astronomy. All we have to do is fill the coal load and then tune the radio astronomy receiver. Both receivers are permanently mounted side by side on the antenna. Everything is under the control of a computer. All we have to do is type in instructions, and the computer does all the rest of the work. Switching from the Comstar satellite to gas clouds in our galaxy can be accomplished in a matter of minutes. There are still lots of interesting problems for radio astronomy. In the Big Bang explosion, only hydrogen and helium were formed. All the other elements, the carbon, nitrogen, and oxygen that we're made of, indeed all of the heavier elements that the things around us are made of, were formed in stars. And the clouds between stars are full of activity, rich in the history of the chemical elements and the origins of life.
My work in communications research is now mostly managerial in nature. I'm presently responsible for the Research Communication Sciences Division, a collection of some 300 scientists, engineers, and technicians. All the work, all the ideas have to come from people. We have people here working on lasers, for example, hoping to use light for communications purposes the way we now use electricity directly. We have people using computer technology in order to provide new kinds of communications between people and machines of various kinds. Others are working on electronic components. What I'm trying to do is give encouragement to these people, to provide focus toward common goals, to take these diverse efforts and bring them together in some kind of coherent and useful result. Thinking back, the things that Bob and I were able to do together were strengthened to a large extent by the fact that we complemented each other. We were different in approach. We are different in personality. And the fact that we are different seems to show, at least to me, that there isn't any one simple model or scientific mold out of which you make scientists. At present, my scientific interests have gone back to the Milky Way, the place that we started our work 15 years ago. I'm trying to put together a story which talks about the birth and death of stars, where those stars are going, what the structure of the galaxy is. The whole question that you get when you look up at the night sky, and you just kind of look up and say, what's up there? What's it doing?
People occasionally wonder why Bell Labs is interested in radio astronomy. It's really quite simple. There's always been a very close coupling between telecommunications and radio astronomy. You're working with similar kinds of antennas and receivers. For some kinds of astronomy, they can even be built into the same telescope, like our 7-meter. Advances in one field continually pay off in the other. It's happened in the past, and there's no reason to think it won't continue to happen.
Then, of course, there's the matter of curiosity. Basic science is, after all, just a form of human curiosity.
Praise silence for Dr. Arno A. Penzias, 1978 laureate in physics, who is now giving an address to the students of Stockholm.
Curiosity is a precious gift which comes to us so naturally that we sometimes fail to appreciate it. Children ask difficult questions. Why is it dark at night? Why does the car smoke when it's cold? We parents experience a feeling of relief when children are finally old enough to go to school and learn to stop asking so many questions. I hope you have not learned that lesson too well in your own schooling.